Hello, fellow problem solvers. So today we're going to be doing a problem from the Canada Math Olympiad 2015, problem number 1. I suggest you try to problem out for a minimum of 10 minutes, ideally 30 to 45, not more than an hour. If you'd like to go along with us, I suggest you give it a go for the next 10 minutes. And here's the first sort of translation of the problem, because I didn't want to write out the whole thing. It says, find all functions from the natural numbers to the natural numbers. Natural numbers start at 1 here. Such that for every n that's a natural number, we have this thing that holds true for f. N minus 1 squared is going to be less than f of n times f of n, and is going to be less than n squared plus n. So let's begin. So how do you do this? I have no clue. It's the first problem, so it tells you it's not going to be too difficult, but let's see what it's about. So first, let's plug in 1. Because this interval, the smallest is 1, and you want to sort of get these first couple of values going, understand what's happening. So we have for 1, 0 is less than f of 1 times f of 1. Okay, and this is less than 1 plus 1 is 2. That's an introductory problem. 1 plus 1 is 2. So this implies, because we're in the natural numbers, then this can only be 1. So this, because a times b is 1, a and b are both natural numbers, we have both a and b need to be 1. So f of 1 is equal to 1. Oh, that was nice. We just got f of 1, just like that. Now let's go for 2. We have 1, that's 2 minus 1 squared, is less than f of 2 times f of 2. Okay, and this is less than 6. What do we do here? Well, not to worry. Let's just see what this is. F of 2 cannot be equal to 1, because if it was 1, then this would be 1, and then this would also be 1. So f of 2 isn't 1. Let's get that straight. And furthermore, f of n is never 1, because then this would be 1 times 1, and it would not be greater than n minus 1 squared for any n greater than or equal to 2. So we have 2 isn't 1. It could be 2. If it was 2, we would be okay. And it cannot be free. But why can't it be free? Or 4 or 5? I invite you to pause for 5 minutes and figure out why that is. And the answer is, well, from here, it holds that it seems that f of n is greater than 1 for all n that are greater than or equal to 2. So if f of 2 was greater than 2, that would imply that we know that actually, we can say we know f of 2 is greater than or equal to 2, which implies that f of 2 needs to be less than 3 and greater than 1. And from here, we have f of 2 is equal to 2. And so we have f of 2 is equal to 2. And now when we look at 3, we're going to put n is equal to 3. And we have, here we're going to have 3 minus 1, which is 4. 3 minus 1 squared, which is 4, is less than f of 3 times f of 3. And this whole thing is less than 9 plus 3, which is 12. How are we going to do this? Here I invite you to pause for 5 minutes and figure it out. Hey, what did you do? So f of 3 can't be 1. Can it be 2? No, because if f of 3 was 2, then this would also be 2. Then we'd have 2 times 2. Oh, no, you don't. No, you don't. You can't have it be that. You can't have it be 1. So f of 3 can't be 2. It could be 3. But we know now f of 3 is, because f of 3, and not only for 3, we know for any n, if f of n was equal to, say, 2, then f of n would also be 2, and then this would be 4, which is not greater than n minus 1 for any n greater than or equal to 3. So that is how we know f of 3 needs to be greater than or equal to 3, and f of 3 needs to be greater than or equal to 3. Right? Because this cannot be, just by extension, because if f of n is greater than or equal to 3 for all n greater than or equal to 3, then it follows that f of n, because this thing in here is greater than or equal to 3, then this is greater than or equal to 3. So that's how you can get that. If this was 4, all we have a contradiction, because if this was 4, we'd have a contradiction. So actually, not necessarily, we wouldn't necessarily have a contradiction, but that means this is going to be greater than or equal to 3, which means that f of 3 is going to be strictly less than, actually, so this times this is going to be greater than or equal to 3 times this. So it means that this is less than 12 over 3. Actually, I might have messed up the 12. Have I messed up the 12? No, I've not messed up the 12. Everything is good. So now this f of 3 is then less than 4, greater than 4 over 3. And then what do we have? This is when you apply this inequality and divide by 3. And now what do we have? Well, f of 3 isn't 2. It's greater than or equal to 3. So f of 3 is equal to 3. Do you see a way for you to now solve this problem? Here's where I invite you to pause for 20 minutes and think, how would you solve this? Now, let me clear the board. So this till now was just a natural progression, sort of like, I don't want to say natural, but I want to say a step-by-step building up our intuition about the function progression. I don't think I've made too many big leaps here. The only maybe big sort of leap that might happen is that I've been playing around the fact that these are natural numbers and not rational numbers, right? If a f of x is between 0 and 2, and we're in the natural numbers, then it must be 1. Like, that's the sort of big idea that we've done here. Now, the big idea here is mathematician is only as good as they know how to use induction, which means what? The idea here is induction. And so the idea here is, let's prove that f of n is equal to n, and it seems likely by now. And here's why it seems likely. If f of n, if we've done f of n is equal to n till some point, it has to be at the next point. Why? Because f of n for every n greater than that, say t, is going to be greater than t. If it was less than t, then both of these would be t. We would have t squared, and here we have n minus 1 squared. N minus 1 squared is greater than or equal to t squared. We have a contradiction. So that's why it sort of makes sense that you're using something like induction here. And this is just n times n plus 1, right? And it's like you're going to be able to push these towards each other. So we're going to prove that f of n is equal to n. We have, so first the induction. The part of the induction is the base case. We have base for 1, 2, 3. 1, 2, 3, 1, 2, 3, 3, 1, 2, 3, 1, 2, 3, 3. And now, assume that you have it actually not just any induction, but strong induction. Which, I've never understood, why don't we always use strong induction? Like, maybe you just want to write less things, but I always assume a strong induction is like just a regular one. Like, why would I forget about all the work I did beforehand? I always want to go like strong induction. So assume that f of n is equal to n for n is equal to 1, 2, 1, 2, all the way through k. And we're going to prove this claim for k plus 1, right? So now we're just proving the claim for k plus 1. If f of k plus t for t greater than or equal to 1 was less than or equal to, what's it called, k, we'd have f of k minus k plus t is equal to what? Let's say some a that's less than or equal to k, and then f of a is equal to a by 2 by the inductive hypothesis. And then we have f of k plus t times f of k plus t is going to be equal to a squared, which we need to be greater than, what's it called? k plus t minus 1 squared, which is greater than or equal to k squared. But this, on the other hand, is less than or equal to k squared. And we have k squared is strictly greater than k squared, a contradiction. So now with this, what does that give us here? It gives us that f of k plus t is going to be greater than or equal to k plus 1 for t greater than or equal to 1. Okay. And now we're ready to tackle our big thing. Now this implies that f of k plus t is greater than or equal to k plus 1. Like this is greater than or equal to. Can I just imply it like that? It's greater than or equal to k plus 1. I can say this, like, because this thing inside is greater than or equal to k plus 1, and then I can apply the same thing again for a different t, right? I would put this as f of k plus t is equal to k plus l for l greater than or equal to 1, and then f of k plus l is greater than or equal to k plus 1. I think I might need to do it like this. I'm not sure. But you get the important thing is that you get the substance, the point here. So now we know that specifically for t is equal 1, we now know that f of k plus 1 is going to be greater than or equal to k plus 1. And now with this, what do? I invite you to take 5 minutes and figure it out. So now we have this thing right here needs to hold, but we know that this is strictly less than, what is this? N times n plus 1. So this is k plus 1 times k plus 2. And now we combine these two inequalities, and we have k plus 2 is strictly greater than f of k plus 1, which we know by this thing from here, that this is greater than or equal to k plus 1. And so it forces that f of k plus 1 is equal to k plus 1, which finishes up our induction. Now, this might be a bit advanced, and if it is, I would really invite you how I would come up with this. And I think right now I've done it till 3. Right, I've played for for n is 1, 2, 3, 4. For n is 1, 2, 3, I've done it here. Now, when I probably did this the first time, I probably went to 4 or 5 until I got, oh, I get the substance, or maybe 6 or 7. It's okay to go a lot of these cases, try a lot of these n, until you get what the substance is. And then when you get the substance on these small numbers, you can go to the variables, which are, I think, maybe for me, a bit less intuitive. It depends. It depends on the problem. It can be harder to go with variables. Sometimes it's easier to just forget about the cases and just like play with the variables somehow. But here it seemed like I actually might get lost sometimes just like playing with the variables right away. So that's why I play with legitimate concrete numbers before playing with more and more variables. And that is how I get to all of these things. So if you're having trouble with this, play around with more cases before trying to do the induction. And the induction is really just formalizing this intuition, saying like, oh, I am using the fact this thing right here can't be less than n. And when it's because that can't be less than n, then this is going to be, that means it's greater than or equal to n plus 1. That means I get greater than or equal to actually n. That means this is less than n plus 1. Like, that's what you're really doing when you're trying these things out in a different way. A cool problem from the Canadian Math Olympiad, problem number 1 in 2015. Very nice problem. And as always, thanks for problem solving.